Encoders are instruments used for measuring angular position of joint axes, typically of the motors that are placed connected to the joint axis of a robot. Last time we saw the principle of operation of absolute encoders. Absolute encoders are made of optical disc with multiple tracks. The number of tracks provides us a measure of resolution of these devices. And from an operative point of view, these devices do not need a homing procedure. So when the robotic system is turned on by means of different techniques, they immediately measure the angular position, so the robot knows which is its internal configuration and can start doing whatever it's being asked for. The alternative is to use incremental encoders. Now, incremental encoders are simpler in construction. There are some applications where the use of absolute encoders is meaningless. For instance, if you want to measure the rotation of the wheels of a mobile robot, you don't need to know exactly the angular position of the wheel. The only thing that you're interested into is how much rotation does a wheel makes in contact with the surface, because this is related to the progression of the vehicle on the ground. So in that case, incremental encoders are the only reasonable solution. For manipulators, instead, they have benefits, simplicity, but also some drawbacks. How do incremental encoders work? Well, they measure incremental or increments of angular position. This is why they are called like this. Again, they are made of a rotating disk. The disk rotates together with the motor axis, typically. They have only 3 tracks, not a certain number of tracks. And the more, the better is the resolution, like for absolute encoders. And each of these tracks, actually there are 2 similar tracks that are called channel A and channel B. You can see here these external rings. Again, there's a sequence of transparent and opaque sectors. And you can count the number of these alternating sectors. And the second channel, channel B, is exactly the same, only it is shifted by a quarter of a so-called electrical period. Why electrical period? Because associated to these 2 sectors, there are the same machinery as in absolute encoder, only much simpler. Namely, there's a photoemitter. So while the disk rotates, this passes through the transparent sector, and it's detected by photoreceivers. Only that you need only 2 photoreceivers here, as opposed to n photoreceiver if you had an absolute encoder with n tracks. Okay. Now, if you count the number of, let's say, the white 1, 2, 3, 4, 5, and 6, while the disk makes 1 full round, you will feel on the photoreceiver 6 impulses. So it's a square wave signal, more or less square. If you're rotating at constant speed, you will see this type of signal, for instance, on channel A. Actually, you don't see exactly a square wave. You will see some kind of approximation because of the electronics. Okay, and the faster you go, you have the same problem as before. So there's an upper limit, and there are also manufacturing accuracy that you have to take into account in order that you have a good incremental encoder. Anyway, while rotating, you feel this train of pulses, and when you have done a full turn, in this case, you have seen 6 times the leading edge of those pulses, and so you can count an increment of 360 degrees. Of course, the more the sectors, the more impulses per turn you have, the more accurate you can measure increments. Okay? Now, why there's a second channel, which exactly makes the same. I mentioned before that this is 90 degrees out of phase, electrical, because you have to count one electrical period, so from here to here, which is exactly 360 mechanical degrees divided by the number of pulses per turn. Okay, so 1/4 of a period is this is half a period, this is 3/4 of a period, and this is a full period. So 90 degrees electrical shift between the two channels. Why are there the two channels? Exactly because we want to understand if we are obtaining positive or negative increments. Okay? So if you look at these leading edges, so if I make here a graph, more or less, this will be channel B. Now, if you look at things from this side, so this is the first part of the signal, so you're an observer, and those signals are coming toward you. Okay? So if you're rotating in one direction, you will see first the leading edge of channel B, and then the leading edge of channel A. If you're rotating the other way, so you're looking from this side, and this train of pulses are coming toward you, you will see first the leading edge of channel A, and then the leading edge of channel B. So you can set up some simple electronics in order to detect if you're incrementing or decrementing, if you're rotating clockwise or counterclockwise. Okay? Now, there's a third channel, which works exactly like before, but it's used only for doing what is called the homing. So for deciding when I see or don't see some image on the detector because of this single sector, which is in this case opaque, you can reason also in a dual complementary way, then you reset your counter and you say, okay, from now on I know where the motor is, what is the angular position in this case, and from there on I count. Okay? So this, of course, depending on where this absolute incremental encoder is placed, typically on the motor side, you should always take into account that beyond the motor, you have a transmission element, you have a reduction of the number of turns per second. So the homing, so the zeroing operation should be made appropriately. We will comment on this now. So essentially, the third track is for setting the zero, whatever this means, the reference point. And from there on, you count pulses. Each pulse, depending on the number of pulses per turn, for instance, between 100 and 5,000, even more in the most advanced incremental encoder. So if you count, let's say, 2,500 pulses in an incremental encoder that has 500 pulses per turn, that means that you have rotated an increment of 180 degrees. Okay? Things are not as simple because there is some improvement that can be made, but essentially this is how it works. Some encoders provide also some additional information which is still related to the angular position, in this case of the motor itself. So those encoders are typically mounted on the motor axis, not beyond the reduction element. So they provide also the phases, for instance, for driving and controlling a brushless AC motor. They need to know in which position the motor is to drive the switching electronics of those motors. But this is, for us, not too much of interest. So let's comment a little bit more on the zeroing operation. So when you turn on a robot which has incremental encoders, and this is often the case, I would say. It's not the totality, but it's often the case, more than 50% of the case, let's say, at least. Then the robot starts automatically a homing procedure. So he has to know in which configuration, so he has to find a reference configuration from which he starts counting incremental angle, okay? So you will see the robot moving one link at a time, so one joint at a time, typically from the last link, then back to the bottom, to the base. So you will see one joint moving in one direction and then in the other direction, okay, till it finds some reference point, some mechanical stop, and then the first time it encounters the Z track, it zeroes the counting. Okay, from there on, he knows how the link is placed. And then it moves to the before last link that is being moved around its driving joint, and it repeats the same procedure. It takes a few tenths of seconds, so let's say 20 seconds, 25 seconds. And when all the joints have been homed, this is the terminology, then you can start operation. It's a procedure that you don't have if the robot has only absolute encoders. It's only for incremental encoders. So now let's look a little bit more in detail on the signals that comes from the three channels. So forget for the time being, or these other signals, which are the three phases that eventually are used by an AC motor. So our interest is on the top diagram, A, B, C. So I already mentioned that there is a difference between electrical degrees and mechanical degrees. One turn is 360 mechanical degrees. One electrical degree is a mechanical degree divided by the number of pulses per turn. Okay. Now, how do you count things? You use some simple electronic, for instance, a flip-flop and a counter. You know how a flip-flop works. Okay? For those who do not know, just as an example, they have two inputs. They have a clock, and they have the standard regular input. And on the output, you find what you have on the input only at the time where the clock goes up. Okay, there's a one switching time, and whatever is in input is found with a small delay in the output and held until the next clock. At the next clock, you see again what you have here, and this is going to be translated into the output channel. Okay? So here you may assume one logic or the opposite. Let's say if you have a 0 here, so you have down this, you're rotating counterclockwise or clockwise. Okay? Now, this is used to sense only direction. So you use this flip-flop to drive the up and down input of a counter. You take one of the two channels, doesn't matter which one, channel A in this case, and this gives the clock to the counter. And the channel Z is the reset for this counter. So every time you have encountered the Z channel, you start counting from 0. And you may have stored in an additional memory the number of full turns that you have done so far. And you can also increment and decrement those numbers. Okay, so it's a multiple electronic circuit. Now, you can, adding some simple electronic, you can improve the resolution of the original encoder, which essentially is related to how many sectors you can put into the optical disc with accuracy, with enough accuracy. You can multiply by a factor of 4 the resolution by performing some processing on the data. For instance, you can take the two channels, perform an exclusive OR, which means taking the two channels and having a 1 if and only if at most one of the two channels is high. So you will have a 0, then a 1, then again a 0, then a 1, a 0. So you're doubling this frequency, in fact. This already could count twice as much as the original signal. But you're not satisfied with this. You take this output and you let it delay. So it's like a flip-flop of this kind, only I realize this with an amplifier and a condensator and a resistance. So in fact, this introduced a time delay by figuring out these two parameters of about 90 degrees electrical. So at this stage, you have here a delayed signal by 90 degrees and the original signal. You do another exclusive OR, and then you can double again the frequency. The final output is the signal C that you see on top, which has 4 times the number of pulses per turn as the original output of the encoder. Okay? So you will use this in order to drive the clock of the counter, so you can count more frequently. So if the original system had whatever, let's say 200 pulses per turn, you will have 800 pulses per turn, and the resolution will be improved by a factor of 4 accordingly. Okay? Now one may wonder, why do I stop here? I can do this over and over. So instead of having a factor of 4, I may have a factor of 8, a factor of 16. What is the limit of this operation? Any idea? Well, remember, it's related to what we have, I tried to sketch here on the blackboard. Those signals are ideally square waves, but in fact, they are smoothed because of the timing needed by the electronics to acquire the energy of photons going from the LED to the photo detectors. So there is some blurring of things, and if you then multiply things, this blurring at some point will be such that you have more noise than signal, and there's no sense of dividing further the timing frame with this technique. Okay? So 4 is the standard solution. Here, this type of operation is also called quadrature detection. It's not used only in encoders, so not only in robotics, actually. And here we have another implementation, a more robust implementation, actually. There you see the two channels A and B. And this implementation assumes that you have a higher frequency clock available. So a clock that has more pulses, much more pulses than those present in channel A or in channel B. It's the same, they are only shifted by 90 degrees electric. Okay? And then you use 2 delay flip-flops, so you generate channel A delayed, channel B and channel B delayed, and then you use, again, exclusive OR gates, and you use one signal with the XOR. Pay attention how you define XOR of more than 2 inputs. One is used for enable the counting, so the clock of the counter, the other for having the up-down input to the counter. Okay? So here you see a fast clock. You have here the 2 channel A and channel B delayed by 90 degree electrical. You see that this clock is much faster than these 2 signals. And then after the D flip-flop, you have the same signal A and B delayed. And then this is the result of the XOR made on the 4 channels. So A delayed and B delayed, or only on channel A and channel B delayed, which is for the direction. Okay? And in fact, if you look at one full electrical period here, so one count without this circuit, you see that within this one count, you have 1, 2, 3, and 4 counts at the output. And to make things more stable, you may add also additional flip-flops. But I mean, I just write this note there for those interested. Now it's not really relevant. So this is just a simple count, again, a different picture, but the same concept. So suppose that you have an incremental encoder that has 2,500 electrical cycles, so impulses per turn. After this multiplication by 4, we will count 10,000 pulses, which means that the resolution is 0.036 degrees. Okay? This is on the motor axis. Of course, if I have a reduction, this will be even further amplified at the level of the driven link. So again, we have to decide if we want to have those sensors mounted before or after the reduction element. Okay? If we mount it after, we have an accurate measure of the links, which is what we really care of. But of course, we don't have this improvement of resolution related to the presence of the reduction. If we mount it on the motor side, we will be more accurate in measuring the link position. But if we have some elastic effects, we will lose this because we are measuring before the transmission. So any elasticity in the transmission is out of the measurement loop. Okay? So there is a trade-off between these 2 aspects. We have seen, for instance, in the DLR exploded joint view, you remember that picture, that because of they were using an harmonic drive, which is known to be an elastic transmission, they had some electronics sensing position on the motor side and other sensor, actually an Hall effect sensor, measuring position beyond the transmission. Okay? Just to make sure that all information is there. Now, this is just a minor slide, I would say, that points out the fact that why we cannot multiply by 8, 16, this idea, because actually manufacturers of encoder may provide you this information. So on the accuracy of their measurement device. So for instance, we may have a period of 360 degrees, but then we may have some error due to the construction and to the electronics, so that we see the next pulse not after 360 degrees electric, but with, let's say, 10, 15 degrees more or less. Okay, so, and if you accumulate this, you may then get lost if you're dividing too much. And then also another error is the phase shift between the two channels, which should be 90-degree electrical. Again, you have plus or minus some mistake. If this is too large, of course, the quadrature error makes this device not useful. Okay, so this should be limited below, well below 35 degrees. Okay, so the fact that the manufacturer is providing you this number, for instance, this plus or minus 35 or 25 degrees, means that these channels are not providing exactly calibrated square waves with the right phase. Okay, so this was about measuring angular position. We have mentioned that there are other systems, but the two that we just discussed are the most common one. Now you can have encoders, for instance, incremental encoders, that may have up to, after multiplication, 64,000 pulses per turn. So they are accurate enough for measuring position, but then they can also be used for measuring velocity. Why is that? Well, this is intrinsic to the digital nature of these devices. So the counters provide an increment, and if you divide this increment by the unit of time through which you're counting things, you have a variation of angle over a variation of time, and this is, for small variation of times, this is approximately a velocity. So the same position sensor can be used also for measuring velocity. Okay, so it's what we call, and this is quite often done in robots, especially now that the resolution of these encoders is very large. So instead of having an explicit sensor for velocity, you use the encoder, and then you do numerical differentiation, like you would think to do. For instance, there are various so-called backward differentiation formula. The most simple one is the Euler method, which says that the velocity at some instant k, so this notation, q dot is the velocity, q dot k is the velocity at an instant which is k times the sampling time, capital T. Okay? So every, let's say, 1 millisecond, you're measuring. So after 1 millisecond, 2 milliseconds, 3 milliseconds, you have an estimate of the velocity, which is made simply by taking the current measurement of position. Absolute or incremental is not important, of course. No? If it's absolute, you have stored the previous measurement, and then you do the difference, and then you divide by the sampling time. If it's an incremental encoder, you have just the increment, unless you want to use a division by a time which is not the clock of the encoder itself. You may do it, but why make things more complex? So this is the standard formula. But pay attention, there are more formulas that may provide a better estimate of the velocity. This is anyway an approximation of the actual velocity. Okay? All this formula may only use the current sample of position and the previous one. Of course, they cannot use the future value, because this is a differentiation which is made online. While the robot is moving, you're processing the data and you're estimating velocity. Okay? So, for instance, this is a backward differentiation formula with 4 steps. So you're using the position, the current position qk, the previous 2-step, 3-step, 4-step before, combined with coefficients that are chosen accordingly to some rule, which, for instance, minimize the differentiation error with respect to polynomial trajectory. If you have a polynomial of order 4 as evolution of position in time, then the 4-step BDF provides you an exact value for the velocity at that current instant kt. Okay? In general, you don't have such nice polynomial profiles, so these are anyway approximation. Of course, the more are the steps that you use, maybe you improve your accuracy, but you don't go beyond that, because if you're using older samples, they don't have any information on the current velocity in general. If the trajectory is not smooth, if there has some sharp changes, sharp accelerations, then the older samples are completely useless. Okay? In fact, this is a general problem. If you don't know in advance the signal that you want to differentiate, in our case the position profile, then you can only use previous samples. But if you know in advance the whole signal, there are techniques which provide you the first derivative, but even the second, the third, the fourth, whatever, in a much more reliable way by using, at the current instant, not only the previous sample, but also the future sample, which are assumed to be known. So if you store a whole position profile, and then offline you process it in order to understand a posteriori which was the velocity evolution, you can do much a better job than doing things online. Unfortunately, most of the time you need this information online. But still, sometimes it's convenient to use other type of digital filters. This is actually a digital filter. Also, the Euler formula is a digital filter. Very simple, but so this type of filtering is called non-causal, exactly because you're using not only previous and current samples, but also future samples. And I think that everybody agrees that if you have these samples available, you can do a better job in estimating derivative. For instance, suppose that this is your signal, and here you have a sharp change. And now you sample this position signal. And you have a period of t. And now here, you're estimating this derivative by using this sample, and maybe also this sample. You fit some polynomial here, and this polynomial may fit well here. And then you take the derivative, and here is quite good. But if you do the same thing here, and you have this data, and this data, so the current data, the previous one, and the two previous one, and then your polynomial will do something like this, and you're estimating a tangent like this, while the tangent is like that. Okay? As simple as that. Now, if you have available also, let's say, two more samples after the current one, and this is possible only if you're processing your data once the motion has completed, so offline, then of course you can use a higher order interpolation, and your interpolator may do something like this, and then diverge out of the 5 point, and here the estimate is pretty much closer to the desired one. Okay? Very simple. So this type of filters there are many of them. One class is the Savitsky-Golay method. And here I have an animation of what happens when you have a noisy signal. And the noisy signal means that, especially if you're moving at low speed, you may have these peaks and additional noise. And in fact, you're moving very slowly. So if you have small increments in a unit of times, one bit more or less makes a lot of difference. If you're moving fast instead, then one count more or less divided by the sampling time, which is always the same, makes little difference. So at low speed, you may have very much noise. So here in this animation, you will see the processing of a noisy signal. You will see that it's kind of oscillating by a Savitsky-Golay, which uses 5 samples centered on the current one. So like in this case, 2 before and 2 after. And you will see I hope you will see it, how this works. So this is the noisy signal, and these are the interpolating polynomial of the 5 data centered around the current one, and this provides locally a good estimate, and then from that polynomial you can do analytical differentiation and estimate the velocity. Okay? Only that the polynomial are changing while the data are changing. So this is just an example of the fact that you may wish to not use an additional sensor for measuring velocity, which is another information of the proprioceptive state of a robot, so the velocity of all its joints, but just process numerically the digital output of encoders. Here is another way of doing things. I hope that some of you have encountered Kalman filter, or will encounter Kalman filtering, which is a way of estimating the state of a dynamic process, in our case, position velocity of the joints of a robot, which takes into account noises, some structural noise, on the measurement of the measurement that you make, and possibly also on the state evolution of your system, meaning that your model of your system is not so accurate, and you model the uncertainty with additional noise. So you have a process that is not known exactly, and this poor knowledge is modeled by noise. Then you take measurement on the output of this system, and the measurements are typically noisy, and you model this noise. And out of this, you try to extract, in the best possible way, the actual value of the state of your process. So eliminating as much as possible noise in this process. And the Kalman filter for linear system having linear dynamics, assuming that the noise is a white noise, it's a Gaussian noise with zero mean, it's optimal. So you cannot beat a Kalman filter under this condition. Linear dynamics of your process, so linear measurement corrupted by Gaussian noise. In fact, noise does not behave always like this. The dynamics of your system is typically not strictly linear, so there are other versions that can be improved over the standard Kalman filter. One of these is the so-called extended Kalman filter, which is largely used in robotics, also in mobile robotics, for instance, for solving SLAM problems. Or there are other type of filtering, like using particle filtering. I just want to show you not the details of this, but just to let you know that there is some other methods for doing filtering and for extracting not only an estimate of the velocity, which was our original problem, but also a better position measurement, because this filtering filters also the original output measure, so the one provided by the encoders. Okay? So the idea is the following. You use the most simple second-order system. You see, this is a system with two states, two-component Xi, written directly in discrete time. So this is at sample k, so k times the sampling time t. You have a state Xi, which is composed by a position and a velocity. And the next position, xk, is the previous position plus t, the previous velocity. This is the first equation on top. While the current velocity is just equal to the previous one. So you don't make prediction on changes of velocity. Changes of velocity are modeled by noise. So the mu is the noise on the state equation, which accounts for the fact that you don't know exactly which will be the next velocity, and so how this will affect motion. And also there is some noise on the state. Plus you have an output equation, and the output equation is the measurement z, which takes only the position as a measurement, for instance, through an encoder, and it adds some Gaussian noise again. Okay? So this is how you model the system, and now on this system, with some hypothesis on the variance and covariances of the noises, remember that nu is a scalar noise, mu is a vector noise, so for the scalar you talk about mean and variance. For the vector mu, you talk about covariance matrices, okay? So you call it Q and R, and then you can write down the Kalman filter equation, which is very simple. It took time to prove its optimality, but it's eventually very simple. It's just a copy of the original system without noise. So you see that this part is exactly that part when you remove mu and ni. So this is the so-called a priori prediction. So you have an estimate x hat at the previous instant, and you bring it farther one step, and you have the estimate at the current instant. Of what? Of the position and velocity. Now, this prediction is corrected by the error that you see. So here is the prediction of the state. This is the matrix that takes the states and provides the output. So this is the predicted output, and this is the actual measured output. So if these are consistent, then this is 0, and so you can just move one step farther your previous estimate, according to the model without noise. If instead, like it's usually the case, you have some mismatching between the measurement and the prediction from the estimate of the previous state, this will drive a correction through a gain which is the optimal Kalman gain matrix. This depends on the covariances of noises and so on. Okay, so this is the basic principle. So you can use a Kalman filter like this to process encoder data and provide a filtered version of the position and also an estimate, a smooth estimate of the velocity. And this is online because you're not using future sample, only the current sample. So for instance, this is just a representative plot taken from a technical paper where the authors were using this technique, and they were also using vision to let's say, qualify the position measurement. So here you can recognize this noisy signal. This is the output of the encoder. This is the filtered version of position as obtained by a Kalman filter, taking the first component of the estimate xi hat. Okay, so this is the estimated position. And you can see that it's much smoother. And these dots are acquired by vision, by an external sensing, and they are hold for one sampling time. So you don't see this, but they are hold like this. And they are slightly in delay. Why? Because the vision system needs time to acquire this information. Okay? So there's a natural shift, but if you could move, let's say, one step ahead the vision data, you would see that they fit well with the estimated position that has removed the noise. Now that you have such profile, you don't differentiate this. This is different from the previous approach. In the previous approach, you have a polynomial function or whatever that fits in a average way your data, removing as much as possible noise, and then from this analytic expression of the interpolator, you take the derivative. Here you have a functional version of the filtered position, but together you have also the second component of your estimate, and this is directly the velocity. So for instance, here you have a typical situation where this spiky are the measurement, not filtered by the Kalman process. So out of this you take some signals like that, and as second component of the filter, you have also this estimate of velocity. Okay? You see that you can remove quite a lot of noise from your data with these techniques. Of course, it's more computationally intensive because this is right at the core of your measurement system. You have question on this? Again, this is just representative. So remember that you may have different way of processing digital data coming from an encoder in order to have estimation of, a smoother estimation of position of the measurement themselves, or an estimation of velocity. Still, and especially in the ancient times, so this is now almost historically, used to have direct velocity sensor, so-called tachometers. Okay? And in some automation application where actually you're interested in controlling speed, and speed is should always almost be constant in different operating regimes, then you still use tachometers, so a direct measurement of velocity. What is the principle? Again, just to have a physical feeling of what are you doing. Again, you're using some coupling between electrical phenomena and magnetic phenomena. So here you have a permanent magnet and you have a rotating spire, a coil, which has some area, sigma, and this rotates at the speed of the motor, so omega, which is the quantity that you would like to measure. Okay? So this is solidal to the motor. Now, while rotating, the flux going across the coil changes. The magnetic field is constant, but the flux is proportional to the angle theta. Proportional. Varies with theta, actually, in a trigonometric way, if you're moving at constant speed. And for the time being, we can consider that this is a fraction of time where velocity stays constant. Okay? So, cosine theta, if you're moving at constant velocity, can be written as omega times t. So you have this type of pulsing, sinusoidal pulsing flux, and the tension that you have on the coil and that you can measure is proportional to the variation. There's a minus sign, just it's not relevant, to the variation in time of the flux. So you have this type of signal. Okay? Now you can see that if sine was not there, there are some constants, so the constant flux and the area of the coil, which makes the tension proportional to the omega. So you have an electrical signal which is proportional to the mechanical quantity that you want to measure. Unfortunately, this pulses at the same frequency of the velocity that you want to measure. So the faster this, the faster is this oscillation. So one coil only will not be a good solution. So what you do, like for motors, for DC motors, you put several coils displaced by some angle. Let's say you put M coils, and for instance you put 3 coils. There are one here, 60 degrees and 60 degrees. And so you have 3 signals like this, but shifted in time. And if you put more, you may have almost a constant signal. And then you can extract omega more easily. Okay? Now, all this happens quite fast. So, but still, you have some residual ripple, even if you add the number of coils, and you cannot add more than too many coils, let's say 8, 16 or something. Okay, so when you want to buy a tachometer, you find some data sheet like this one. This is a tach generator. It's bidirectional, so it's able to measure velocity in one sense or the other. When it rotates at 1,000 rounds per minute, it provides an output voltage in a certain range. Here you see that the ripple is less than 33% of the peak-to-peak value, so of the oscillating quantities. And again, they use internally to the device some filter, which has a bandwidth of 72 kilohertz in order to eliminate some of these ripples. It's quite tiny, 113 grams. The diameter is 2.9 centimeter. Of course, you may have slightly larger, but in general, these are not large. It's not that if you need to measure high speed, you need a bigger tachometers. This is not the case, okay? And then again, like all sensor devices that we have mentioned, you find linearity error and stability with respect to temperature. So all these parameters that qualifies the quality of a measurement device. And the last thing that I would like to show you is here, driving torque. Why do you see this? This is not a motor. So why you see a driving torque? So you should interpret this, apart from the units which are not standard international. So I provided you this conversion. So this is 1.75 millinewton meters. This means that if you mount this tachometer on the motor axis, this becomes part of the load. So you cannot accelerate the useful load, you have to accelerate also the tachometer. But this is minor, it's really minor. Okay, so only a very millifraction of the output torque of a motor is spent on having on the motor axis the tachometer itself. Last proprioceptive sensor that I want to talk about, and this is new slides with respect to last year's, are accelerometers. I'm doing this because accelerometers are being used in several contexts in robotics. They are used for identification of dynamic models. They are using for compensating vibration of flexible structures. For instance, very long links, like in the space shuttle. So there's some use. By the way, accelerometers are used in consumer electronic even more intensively than in robotics. So accelerometers were certainly inside the body of the Sony-legged robot dogs, but they are also in as MEMS accelerometer in your smartphones. Okay? Why? Because you need to sense the acceleration of gravity. For instance, to change the landscape of your view on the screen. Okay? So there are actually several types of technologies used, mostly piezoelectric. Some are piezoresistive, and some are capacitive. And the capacitive one are the typical solution when you're doing MEMS implementation. So solid state implementation of these accelerometers. Okay? Now, the principle is measuring. How do you measure acceleration? You're measuring inertial forces. And from this measurement, you infer acceleration. Okay? The unit of measure are, of course, meter per second square. We're talking about linear acceleration, not angular acceleration. Actually, it's quite difficult to have an angular accelerometer. Most of the cases are concerned with linear acceleration measurement, either along one axis or along multiple axes. Typically, three-axial accelerometer measure along X, Y, and Z. Okay. Sometimes you don't find these units. You find non-SE units like Gs. So you have an accelerometer that measures, for instance, 3G, means 3 times 9.18 meter per second square. So this is a convenient notation in this case. The main difference between piezoelectric and piezoresistive and capacitive is that piezoelectric accelerometers are not able to measure acceleration in static condition. So they are not able to measure static acceleration like the gravity field. If you have something that vibrates, so acceleration is changing over time, down to a low frequency, you can still measure them with piezoelectric accelerometer. If you're really not vibrating the structure, but you have only the constant acceleration, then piezoelectric accelerometer do not provide any output. Okay, and you need piezoresistive and capacitive. In fact, MEMS are of the capacitive type, so they go down to the static or continuous acceleration. Okay. Now, what is the principle? Here I have a tiny animation that should, if I'm able to, yes, it goes. So you see that you have a chamber, you have a mass. Here you have a piezoresistive material. So when compressed, it changes its resistance. And so if you put this into a circuit, you will see a change of voltage. And then you see that when you are accelerating things, this mass pushes inside the box against the piezoresistive material, and you see some voltage as a result in the output. Very simple idea. You don't have contact. So this is this is the accelerometer that you mount, for instance, on one link of the robot. So when the robot is moving, this base is accelerating, and you have a measurement in this direction. And if you have a 3-axial accelerometer, you have inside the device itself, you have 3 devices like this. And possibly they should not be coupled so that you can measure independent components separately. So, even if you have an integrated solid-state implementation, the principle of these devices is very similar to this traditional so-called seismic accelerometer. Okay, so we just study a bit the behavior of this. So this is the box of your accelerometer, and this is how it would look like with a section that shows the single component inside. So inside this, you have a suspended mass of known value, of course. M is known, and it's suspended by elastic spring of known stiffness K, and it damps its motion with a damper with known damping coefficient D. Okay? Now, this seismic mass is connected, and there are different types of connection. For instance, in the previous slide, there was this piezoelectric device material placed beyond. But anyway, this is the sensing device which measures some variation of the position of this mass. Okay? And then outputs some estimate, AM, of the acceleration. And this accelerometer is mounted on the surface of the body that you want to, for which you want to measure the acceleration, let's say in this direction. Okay? This may be the vertical, horizontal, it's a generic direction. So you have this body which is accelerating, and the acceleration is a whatever, some variation of absolute position z, or this may be a vibrating body. You can mount accelerometer on the structure of a bridge and test things, or inside some devices, some transmission element to check if there are excessive vibration in the transmission, which will eventually lead to a fault in the bellow devices. So, now how does it work? Well, we should write some balance of inertial forces for this device. So when I have an acceleration in this direction, this mass undergoes this type of acceleration, which is the one that we want to measure. But in fact, if I'm accelerating like this mass is accelerating in the opposite direction. So I will see a y double dot change. Okay? So the equation is, this is the forcing term which contains m, which is known, but a, which is unknown. And this is what I can measure. And while this mass is oscillating inside the accelerometer, this is governed by its inertial force, the damping, and the stiffness with respect to the y equals 0 is the equilibrium of the spring. So in that case, there's no force. And then proportional in a linear domain to this deformation y, we have the measurement am. Okay, very, very simple as principle. Now, these are differential equation. Now we are, since they are linear, so we can use Laplace transform and convert differential equation in time in algebraic equation in the Laplace domain S. So in place of each derivative, you have a factor S. So you have ms squared ds plus k. And here you have m. And then you bring in also the kt. And so you have a ratio between the Laplace transform of the signal that you want to measure and the measurement output, which takes this form, or if you prefer, this form with the denominator as a monic polynomial with coefficient 1 in front of this. And now you can do the standard Bode diagram of this transfer function, which is the transfer function of your measurement device. Nothing strange. And you will see that it's a second order system. So you will have some behavior like this, then you have a resonance, and then a decrease at 40 decibel per decade. So you have a resonant frequency, and here you usually define a bandwidth at minus 3 decibel. Here I didn't use the decibel scale, just the proportional scale. So this is 1, and it's 0 dB. This is 1 over square of 2, so it's 0.7071. It's minus 3 dB. So this is the typical bandwidth. But because you have here a large resonance in these systems, then the useful bandwidth is computed like this. It's just when you want to have a fidelity up to 10%, you compute the maximum frequency, and this is the so-called useful bandwidth. So you can measure acceleration components up to this frequency. Okay? Now, if this was a ceramic accelerometer, this was going toward 0 frequency, keeping the constant value. Of course, you can adjust kt such that kt is equal to k over m, so that this has unitary gain. So at 0 frequency, this is 1, and then it's 1 up to the resonance or so. Okay? Now, because of the fact that there are other phenomena that are not captured by that model, so that model is only valid from here beyond. Here you have some leaking effect, and when you go toward the omega 0 frequency for your acceleration, so for instance constant acceleration, you don't have any output for piezoelectric devices. Okay? So this contains more or less all aspects. For instance, for piezoelectric, you cannot use it for measuring acceleration which are lower than typically 1 hertz. And for MEMS accelerometer, you have pretty much the same principle. These are capacitive, so this is a frequency response going, well, here from 1 hertz, but even beyond, you have still 0 decibel, so unit gain. Then you have some resonance, and then you have the same behavior as before, but you don't have this leakage at low frequencies. And this is just a microelectronic picture of how it works. Essentially, here you don't see well this slide, but you have a cantilever beam, a micro cantilever beam. Here we are talking about 10 micrometer. This is 10 micrometers. And then you have a resistor and you have a substrate, so you have kind of a mass which is oscillating, and there's a flexural stiffness due to the cantilever beam. And so the principle is more or less the same as in the seismic accelerometer, only at the micro scale. And this is an idea of MEMS accelerometer. This is I think it's 5 cents US cents, so it's like 5 euro cents. So you see that the accelerometer is much smaller. This contains also some electronics, and this is a 3-axis accelerometers measuring up to 3G, so up to about 30 meter per second square in the 3 direction, low power, and it includes also some conditioning electronic in order to have a filtered version of this. So let me conclude. No matter which accelerometer you're using, how do you use it when you're talking about robots? So, for instance, this is an industrial KUKA arm. It's a medium size, 6 degrees of freedom with offset. And here on top, this box here is the sensor that was mounted at DLR. We have a joint paper in 2007 with that group. And by measuring this acceleration in 3 directions, we could estimate the acceleration at the joints. And from this information, we could avoid to resort to full information on the dynamic model and control the motion of this robot in a reasonable way, I would say. Okay? And this is because this robot used epicycloidal transmission, so transmission which are in fact elastic, so that the measurement on the link side becomes part of the full state of the system. If the system was fully rigid, remember, only position and velocity of the joints makes up the full state, and the acceleration becomes a function of the input torque. Now, since you have elasticity between the motors and the links, you have a second-order dynamic model for the motor, second-order dynamic model for the link, so you have a fourth-order dynamic model, so the state will be position, velocity, acceleration, and jerk. So you have an accelerometer which can measure one of the components of the state. Okay, so pay attention to this, because otherwise you would run into non-causal problem, so-called algebraic control loop, when you're trying to control your system using a measurement which depends on the control that you're applying. So you don't know which comes first, and you have a loop. And this is really sensitive to instability problem. If you have elasticity, then the accelerometer can be used to measure part of the state. So it's like encoder or tachometer for measuring position and velocity. Be aware that you're measuring some link acceleration, not a joint acceleration. And you need some transformation, which is essentially related to the differential kinematic of the arm, to relate a measurement of acceleration in some point of the link to the acceleration of the joints, of the 3 joints in this case. Okay, and this is one use. Here, there's another use that I found in a recent paper, 2011. At the Technical University of Munich, they have built a humanoid. They call it bioloid. I don't know if this is correct. And on the arm, they have mounted these devices, TM341, they call it. They are tactile modules. So they are used to sense touch, but on top of them, they have mounted also accelerometer. And when you see the frame, this frame is aligned with the 3 axes of the accelerometer. And here you have 2 accelerometers mounted, one on the shoulder and one in the forearm, like this. Okay? As part of a more wide sensing structure. And finally, here, there's another example, a 3-axial capacitive accelerometer mounted on an ABB robot. Actually, there's a tool here, and on top of the tool you have the accelerometer so that you can measure vibration while doing contact task with this tool on some metallic surface. Okay, there's a problem here because when you mount this accelerometer, you have to calibrate. You have to know exactly in which direction you're measuring acceleration, because this information is important for controlling motion. Okay? So as all measurement device, you have some calibration problem. So I think that this is a good point where to stop. So we have completed proprioceptive sensing. On Friday, we will start one fundamental topic, which is direct kinematics. So we go to the mathematics. And in the second part of the lecture, we will start looking at exteroceptive sensors.